Okay, welcome to the fourth example in review of statics. The question reads, for the step ladder shown in the figure below, the front and rear side rails have a length of 8 feet. A tie rod or a spreader has a length of 2.5 feet and is halfway up the ladder. A person weighing 192 pounds climbs 6 feet along the ladder. Assume the floor is frictionless and neglect the weight of the ladder. Determine the tension force T in the tie rod and the forces exerted on the ladder by the floor at points A and E. Note, to make the question a bit easier, isolate the parts of the ladder to apply equilibrium conditions and use 2 dimensions to simplify the geometry of the question. Okay, perfect. So we're going to start with givens, as you should know by now. And in terms of what we're given in this question, we're given straight up that the weight of the person, not the mass, the weight of the person that is going 6 feet along the ladder, if this is 8 feet, the ladder is in 8 feet this way, it's 8 feet along the ladder, so it's this way. But anyway, 6 feet, the person's right around here, right there, and they weigh 192 pounds. So the weight of the person is 192 pounds. We have a bunch of dimensions, but we're just gonna draw them on a diagram, not a free body diagram, just a dimension diagram, just to, as the question said, simplify it in 2D. So we're just gonna draw a diagram as if you're looking at the ladder from that angle. So if we draw it, it's not curved, so it's supposed to be like that. There we go. Perfect. And if, for example, you have the tie rod around here, we know that the tie rod, or I'll keep it nice and zoomed out, the tie rod is 2.5 feet, right? And we have points C over here, points D over here, points B over here, and points A and E. The ladder, in terms of length, from here to here is 8 feet. However, the ladder, where it meets the tie rod, so the tie rod is halfway up the ladder, so this is 4 feet. And as we said, the person is around here, so 6 feet. And we're just going to quickly draw all that down. That's way too big. So this is 8 feet. Halfway up is 4 feet. And then our good brother is around here at 6 feet. Perfect stuff. And that's, when we get to the free body diagram, that's where we're going to put our weight force, right? And they're only on one side of the ladder. One thing that we're going to realize later is that we need a bunch of angles. And we might as well just calculate them now. And more specifically, we need this angle theta, and we need this angle phi. Using a bunch of, and I'll even write it down, if you want to find the angle theta, which is the same thing over here, with similar triangles, this triangle and this triangle, if you want to compare it. But anyway, cosine of theta is adjacent over hypotenuse, so 1.75 over 4. So this is 1.75 and this is 4. And then from that, you can extract theta to be about 71 degrees, so 71.79 degrees specifically. And since all the triangles, or all the angles within a right angle triangle, are equal to 180, you can further find that phi ends up being 18.21 degrees. Perfect. So you have all the dimensions that you basically need for the question. All that's left for givens is the notes. And they're just 2 simple notes that can be extracted, and that is that the mass of the ladder is neglected, as well as the friction force, or the friction force of the ladder with the ground. So these 2 are neglected. Perfect stuff. Okay, so now we move on to givens. Let's bring the black color. Or not givens, my bad, unknowns. In terms of unknowns in this question, the question asks us to find the normal force at point A, the normal force at point E, as well as the tension force within the tie rod or the spreader. Perfect. So now, obviously and naturally, we move to free body diagrams. And what I'm going to do, I'm going to draw the free body diagram for this one and this one separately. So let's do that right now. So step 3, we're going to draw FBD. And if we just draw it as blocks like this, I think it'll be much easier. So like that, and then, for example, like that, right? I'll label the points quickly. You have, this is C, this is C, this is A, this is E, this is E, D, and B. Perfect. So what forces? Naturally, obviously, we have our normal force at A, which is what we're trying to find. We have our normal force at E. and we have our tension force, right? Our tension force is what we're also trying to find, and that is also equal to the tension force on the other side. Perfect stuff. What other forces do we have? Well, we do have one force, and that is right up here. You have the force of this side of the ladder acting like this, and this side of the ladder, and that can be drawn like so. And you only have these forces in the first place because you're sectioning the ladder. Previously, when it was like a full body, you don't take these internal forces into account. But since you're sectioning it, since you're separating these pieces, you have to take into account basically the force of the left side on the right side and the right side on the left side, and that's represented like so. We can split it up into x and y components, so fx, fy, and fx, fy. And if this is our plus y, and this is our plus x coordinate system. Perfect. We have one more force, and that is the most important force, what the question is talking about, basically. Our good brother that's going up 6 feet up one side of the ladder. So we have to take into account that force, and it's only going to be on one side of the ladder. It's not going to be on both sides. So if we say 6 feet is about right there, so 6 feet, we can say that the force is, or the weight of the person is right here. Perfect. We have everything we need to move on to like summations, but to make it a bit easier, like I know we have the dimensions up here, and I'm not going to put them over here, but I will put the angles. The angles, it helps you see the, like when you do summation of the moments, it'll help you see it better. So that's phi, that's phi. Perfect. Okay, we can start the summation calculations, and remember we're going to do it separately for each side of the ladder. So sum calculations. Perfect. Okay, so for the left side, we're going to start off with that. We have the sum of the forces in the x direction, and the only forces that you have are this tension force and this negative fx force, right? Same thing with the right side. I'll do both of them in one go. But this time on the right side, the fx force is going to be positive, so take note of that. So let me jot this stuff down. Perfect stuff. Okay. Now summation of the y's, and the y, like the sum of the forces, is basic stuff, so you know, don't stress too much about it. So this is NA, you have WP, and you have FY, right? Similarly on this side, you have the same thing, but you have NE on this side, and you have FY, but you do not have WP. It will be very wrong if you put this weight force on both sides, so please take note of that. So what did I say? Okay, yep. This is actually plus sum of the forces of the y is equal to NE plus FY. Perfect. Now we get to the fun stuff. The fun stuff is the moments. Where the heck am I going to take the moment? I'm going to do it separately. I'm going to do this one separately. I'm going to do this one separately. But where? Which point? Am I going to do the moments about C? Am I going to do the moments about B? If you do that, God help you, that's not going to be good. Or where are you going to do it, basically? And how do I know where to do it? Well, you go back to unknowns, basically. What you need in the question and what also will help you is what you have in the question. Okay, if I take the moment about point A, and this is the same for both sides, basically. If I take the moment about point A, the moment equation is this, basically. From this equation, my R for NA is going to be 0, so therefore this force cancels out. So I'm basically getting rid of one of the unknowns that I want to find. So that's immediately a no-go. I don't want to do that because that'll get rid of the NA force, which I want to keep in my calculations. Okay, if I take the moment about point B, similarly, that same thing will happen. I'll get rid of the tension force, but I want to find the tension force. If I take the moment about, if you do it here, I don't know, good luck, but you're still going to get rid of not something that you want to find, but something that you already have. You know that this force is equal to 192 pounds, so you don't want to do that either. How about FL? Well, FL is pretty useless to me at this point. Like, it's not in my unknowns. It's not, I don't know the value. So most likely that will be the point where I want to do the moment about. And it's also weird, like, relative to we have the f and x, like we have the xy components, but like, I don't know, the better explanation is basically that you don't know the value and you don't want the value, so most likely take the moment about that point. Yeah, okay, perfect stuff. So with that logic, we're going to take the moments about point C, and we're going to say counterclockwise is positive. And let me get this thing in frame here, and I'll explain it once and then write everything down, and this explanation will also be the same as this. So I'll explain it once. Okay, perfect. So we determined that we're going to take the moments about point C, but what forces are going to cause a moment about point C? Well, all three of them, but only their components. What do I mean by that? Okay, let's take WP into consideration first. If, remember, the moment equation is R cross F, if this is our R, right, this force isn't our F, because remember, we're doing it about point C. Instead, the component of the weight force is going to be our F. This is our R. The component, this component, remember, and this is at a 90 degree, this component of the weight force is going to cause the moment. So we have to take that component into consideration. And this is if you want to see the proper diagram. How do we find this component? Well, we have the lovely angles. And I'm not really gonna explain the angles because that will make the video half an hour long if it's not already. I don't know. So yeah. But long story short, this is the component we want for WP. For the tension force, this is the component you want. If you want to see it, I should have made it longer, but it is what it is. That's the component that's going to cause the moment. And remember, this is a positive moment because we said counterclockwise is positive. And then lastly, for NA, this is the component that's going to cause the moment. Perfect stuff. So we're going to jot everything that I said down, and it's very similar to the other side. Okay, perfect. So again, recap. The NA force is going to cause a negative moment. Remember, because it's counterclockwise, so it's going to be negative. So we're going to say in our moment calculation, negative NA. Are we taking into account the full force? No, only the component. And if you do some lovely trigonometry, you're going to get that the component we're looking for is sine phi. Okay, am I done? No, not yet. Because we also have to take into account the distance. Remember, moment is equal to R cross F. We have the F, we need to find the R. The R for this case is 8 feet, right? Because it's NA, it's 8 feet away, as the question said. Perfect stuff. So we're going to put that down. 8 feet. Perfect stuff. Now we do the same thing for the other two forces, and if you do the same thing, and remember these two forces will both cause a positive moment, you will get that that the tension force, or the component of the tension force, is T sine phi. It is a distance, or my bad, T sine theta, and it's a distance 4 feet away, and lastly, you have the WP force, and to find its component that will cause the moment, you have to take the sine phi, and then that is 2 feet away from point C, and then again that's equal to 0. Perfect. You do the exact same logic to the other side. You take the sum of the forces, or the sum of the moments, and positive is counterclockwise is equal to 0. You'll get that the tension force on this side causes a negative moment, and again it's sine theta. Again, it's 4 feet away. And you have the normal force at point E, but this time it causes, like as opposed to the one we did before, the normal force at point A, this one causes a positive moment, because it's shifting the beam or the ladder counterclockwise. Perfect stuff. So basically, now you're done. All you have to do now is try and find your lovely unknowns by doing, I don't know, elimination, substitution. You can use a matrix if you want. Endless possibilities of fun. Yeah. But let's just clean up these equations a bit so you know what to deal with. We have three unknowns. We want three equations. This is basically useless to us. This is t is equal to fx. Similarly, in this way, t is equal to negative fx. So that's not really useful to us. Here, this is kind of useful. We can say if, or actually, let's do this side first. If we say that ne fy is equal to negative ne, we can plug this guy in for fy. Perfect. And we already know that WP is 192 pounds. So if we do that lovely logic, we will get this equation, or one of our first big equations, and that is that NA plus NE is equal to 192 pounds. Okay, that's equation 1. Equation 2 and 3 are this guy and this guy. Very, very simple stuff. And I'll even write them down. So negative NA, or actually negative 8NA. Oh my god. Sine phi plus 4 t sine theta is equal to I don't want to do this math in my head. Let's just keep it as 192 times 2 sine phi, and this is negative. Similarly, for this equation now, and this is your equation 2, for equation 3, you're going to have NE perfect. Hopefully that is right. I will double check that. If not, I will have to re-record that. But those are your three equations. You can plug this into like surprisingly, like you can even plug this into like a calculator. Calculator can solve like these linear equations. Because you have three unknowns and three equations, your calculator can actually solve this like a normal scientific calculator. So unless you want to do like a matrix or whatnot. But you can solve this with matrix, elimination, substitution. Eventually, what you will get is that your tension force is equal to 47 pounds. Your normal force at point A is equal to 120 pounds. And your normal force at point E is equal to 72 pounds. And that is your answer.